All right, so now moving on to our second keynote of the day is going to be Jorge Nocedal. So as many of you might know, optimization is one of the key factors that's made machine learning successful. And so Jorge Nocedal was born and raised in Mexico. He obtained his bachelor's in physics here at the National University of Mexico. He then pursued a PhD in mathematics at Rice University. He has won numerous awards in the fields of nonlinear optimization, applied mathematics, and operations research. He was named an ICES highly cited researcher in 2004. He received the George Dantzig Prize in 2012, the Charles Broyden Prize in 2009, and he was also named SIAM Fellow in 2010, and in 2017 he received the IFORM's von Neumann Theory Prize, amongst many others. He is well known for his research in nonlinear optimization, and is notably the inventor of the LBFGS method, a limited method of a variant popular quasi-Newton method, FGS. Many people here might know him from his book Numerical Optimization, which is the most highly cited work on continuous optimization, and it's actually one of my favorite books, so very recommended. So please give an applause to Jorge Nocedal.
I forgot there was a microphone. Thank you to all the young people who are organizing this event. It's full of energy, it's full of enthusiasm. This is what we need. Something that I think you didn't mention, thanks for the introduction, is that after I got my PhD, I came back here to teach. So I was teaching at IMAS, just across the street. I was there for 3 years, doing, PDEs, optimization, and so on. And at that time, enthusiasm was as big as it is now for other fields, right? So it's a pleasure to meet all the Mexicans and everybody else who's here. And I'll talk a little bit about optimization. So we're going to go back from high-level societal problems to the structures, questions about structures of neural networks, and so on. I will just make one comment about the question about how can we reduce inequality between countries. Because I'm a very simplistic person, my answer is just 2 words. But I think it's something that has been lacking here and lacks in the Hispanic community in the US, and that thing is value education. And I have not seen sufficient improvement in that. And it's so notable when you meet Chinese students and how society values education and how it pushes it. We have to do more about this. This is my very simplistic way of how one particular type of people can move forward, right? All right, value education, it's a lot of fun. In addition to being economically. Now, I'm going to give a talk about optimization geared to reinforcement learning, derivative-free optimization. But before that, given the discussions that I had yesterday, I thought of putting a few controversial statements on the board so that Joshua can get other technical questions. Or all of you can think a little about this, right? So the first statement is, it seems to me that people who develop neural networks got really lucky. Now, why did they get very, very lucky? Well, they were thinking about certain functions, certain structures that would be good at creating representations. And then this idea came that they call backpropagation, which really meant it is possible actually to optimize the parameters of such a complicated network by means of a gradient-like method, right? This is a common situation in scientific computing. Once you have gradients, you get the possibility of solving really large problems. Without them, you cannot. That's going to be the second part of my talk. So why did they get really lucky? Because I don't think it was clear, and maybe it's still not clear, why the minimization of that problem, the optimization of those parameters, which is a non-convex, non-linear problem, can actually be solved. So, it could be the case that every time you change the data, you get a different solution. And just to emphasize this, all my career has been about non-linear, non-convex optimization. And it's been really fun, because the Russian school of optimization, Nemirovsky, Nesterov, they were studying convex optimization. And for them, the world is, there is a solution to the problem. and you can find out what the speed of the algorithm is going to be in complexity analysis, and everything is very beautiful. What happens if a function is non-convex? Then where are you going to end up to? Why are people doing non-linear, non-convex optimization? Where are they doing it? And the truth is they're doing it all over the place. People are designing airplanes, chemical refineries, everywhere, designing glasses and so on. But how can you possibly do that? Well, if you have some progressive glasses there, we can optimize them starting with the design that you have. And we hope that, we're going to in a basin of a minimizer where it makes sense. So airplane design, this is done all the time, right? You have a fluid flow, and you want to make sure that the shape of the airplane is such that you minimize drag. You have certain properties, right? How could you possibly solve? These are nonlinear fluid equations. Well, you start with a very good starting point, and you end up there. And the joke I always used to make in class when I was teaching is you do not design an airplane by taking a block like this and then saying, I want optimal aerodynamics, let the optimization do all the work. It won't happen, right? But here, the optimization is doing a lot of the work, right? So they got lucky, I think, right? So just to emphasize this a little bit more, you know that Minsky and Papert wrote a paper criticizing the perceptron, and they keep writing about this. If you go to the 1961 paper, he says, I doubt that any simple mechanism like hill climbing, gradient methods, will find a means to build an efficient and general purpose machine. Okay, fine. Then they went on in 98, in their second book, they're still saying, if we can detect relative improvement, derivatives, then hill climbing may be feasible, but it requires some structural knowledge of the search space. Unless the structure meets certain conditions, hill climbing may do more harm than good. Okay, people will say, well, they were wrong, right? But what they were bringing up was very real. There was some structure. It was possible for hill climbing to do all of this. And not only deal with non-convexity and non-linearity, but with a high dimensionality. Optimize a nonlinear function, which is non-convex, in a million variables. There's an extremely difficult problem, right? But what happens? Well, the practitioners found out that if they run the stochastic gradient method with some initializations and some tricks, it tends to get to the same solutions. And I remember asking Yann LeCun for many years, do you get the same parameters? No, I don't get the same parameters, but I get the same solutions. I get the same predictors. You're getting that. Well, you're lucky. How, in this space of so many minimizers, we do. Now, there's a lot of work. Now, for the mathematicians, there are papers coming all the time. What can I explain about these functions? Are compositions, right? Compositions of linear functions and piecewise linear functions. What can I say about them? So there's a stack of papers saying, for one layer neural network. And there's some other interesting work that say overcapacitating makes the optimization easier. And this is a general principle in applied mathematics that lifting the space makes things possible. And differential equations, often it makes things stable, right? Okay, so optimization is working. Let's hope that it keeps working. But a valid question, this is backwards, right? The one that goes forward is the one that goes backward? Yeah, okay, this one. Now suppose that someone figures out how to solve partial differential equations using neural networks. Well, that particular function that you're going to find out is probably very different from the function you're using for doing image classification. How do we know that you can actually optimize that function? Well, hopefully, probably because neural networks have been working in a number of domains, but there is no guarantee. So that continues to be an issue of this kind. And the other thing that I was going to mention here that was not part of my slides is there's a lot of interest in saying and thinking about where can I take machine learning into other domains? Can I substitute laws, physical laws, by a neural network? Or can I combine them? And one of the most popular topics is called physics-inspired neural networks. There's a lot of people working on physics-inspired neural networks. What does that mean? Well, I don't know, but what has been done? And I want to mention one work that has been done, because you hear about a lot of people having success in material science and so on. A lot of that is imaging. They're taking results that we know work, taking imaging, and clearly that works, right? So there is a work, Professor Brown Janikati, a name like that. He's solving partial differential equations with neural networks, or so he says, right? And so the idea is a neural network is just it's a function. And the set of parameters that you choose form a variety of functions. So it's a basis for a space, and that basis may contain the solution, the actual solution of that differential equation, right? And so physics-inspired would mean maybe that in the neural network architecture, you're putting knowledge that you know about that domain, right? But that's not what they do. What they do is they have the PDE, they have initial conditions, they run the neural network to try to make the prediction and compare it with the result that the PDE would have given you. So the PDE is a residual, and you do least squares. And then you find out, optimize the parameters so that it gives you the same properties as the PDE would give you, right? So in this sense, it's not physics inspired or physics based, but it's physics constrained neural networks. Maybe it's interesting, probably will be quite limited. There are papers like that. I would not recommend to reading them now, because it takes you a long time to find out where the difficulties are being circumvented. But that's interesting. That's really promising. The set of functions that can do powerful things. So finally, what are neural networks? In its simplest form, a linear function, then a ReLU function, piecewise linear function, and then a composition of this over and over. Now, another basis is just the basis of polynomials. But this particular basis has proven to be very useful. It is known that that is the case, right? So we have a function. They can create certain sets of functions. Let's imagine that it's a variety like this. And you have a certain task. And you want to find within this possibility that neural networks can give you the one that is going to be able to do that task. So it's a projection. You want to find, over here, the best function that gives you that. And that's a nonlinear projection. In general, projection is nice. Linear projection, boom, there goes on the board. If the constraint is nonlinear, the projection requires iterations. And how do you do multiple projections? By means of optimization. So the optimization algorithm is trying to find within this variety the function that does the best job. But nobody knows that this is done to optimality. So it turns out that doing some sort of optimization helps. And I don't know if anybody has any complaints about what I said. Okay. I was expecting. So this is the real talk. Derivative-free optimization, zero-order optimization methods with applications to reinforcement learning. My student Albert Barajas did a lot of this work here. Some of you know him. It's been published. Some of what I wrote here has been published in SciOp recently, and the work on reinforcement learning, we're doing that now. So suppose we want to minimize a nonlinear function using only function information. You do not have derivative information anymore. Now you're really handicapped. And now suppose that in addition to that, every time you evaluate the function, you get noise. You don't get the right function value. Question, is there today an optimization algorithm that can solve this problem with the number of variables is in the thousands? And to my knowledge, the answer is no. And such an algorithm would be needed in reinforcement learning. Such an algorithm does not exist now, and I'm going to propose one that works in the thousands of variables, not in the millions of variables. So where are applications where we want to solve an optimization problem using only function values when in reinforcement learning would be a case? And there are many scientific applications where this occurs. All right, so if you want, let's get, and see the problem precisely. I want to minimize a function. So I use my hands a lot, right? It's a non-convex function just by you telling me function values. My function is phi. I'm going to assume that it's smooth. Now, neural network with ReLU functions is sort of smooth. Well, it's smooth, and I'm going to have errors every time I evaluate the function. I'm going to try to get a gradient. Without a gradient, I don't know where to go. So we're going to get an estimate of the gradient, but it's going to have some noise. So the true problem is to minimize the objective function phi while only observing the noisy function f. In contrast, in neural networks, where everything was so beautiful, we don't need derivative-free optimization. Everything works out sort of perfectly in that environment. You have your empirical risk, the composition of the prediction and the loss function, and you can decide to make a simple, inexpensive approximation of your objective function, right? So you have this complicated objective function, make a simple approximation to that, and get the exact gradient of that approximation and move. And they used to call it, let's nudge the variables a little bit. That's normally not the way you do optimization. Say, if someone is doing a fluid flow simulation or materials, you don't just give it a few data points, integrate the model, and with that make a change. You have to give it a lot of information so that what you get is meaningful. Just think about the weather forecast. So if I just have a new example, it is not going to work, right? But here, it works that way. So you're nudging the optimization in this way with the stochastic gradient method, and you have the exact gradients, and things become very high scale and they work. So that's very nice, but this benign representation will not exist, for instance, in reinforcement learning, where things are a little bit more messy. The reward functions, the action models, so on, may even be discontinuous, right? We may not know them well, they may be black boxes. And so there are two main approaches that people have been using in reinforcement learning. In reinforcement learning that uses neural network policies, right? One is the policy gradient algorithm. Here's a formula, a well-known formula, by which you can compute the gradient of that function by doing some expectation. You have to do some sampling in order to do that. And the other way is to do derivative-free optimization. Try to do reinforcement learning without computing the derivatives of the problem. Okay, so how do you do derivative-free optimization? Let's think about the simplest black box. So some chemist has got a really nice simulation. There are some parameters, and you want to get it really right. All you see is you tune, and you get the result. You're not allowed to see anything inside. How would you do it? How would you do optimization of that function if it's not linear, it's noisy? Well, if you go to our friends, the Russians, the complexity school said, well, in the worst case, the best thing you can do is sample at random. Sample a lot, find the function, smallest function value, and move there. That algorithm, from the point of view of complexity, is very good. From a point of view of computation, is really bad. So you can just keep sampling, and every best function value, you move there. Clearly, you should be able to construct something better. If you evaluate the function many times, you construct a model and use that model to tell you where to move, right? And so, really, the key here is not to be blind. If you have observed the functions in various ways, you can do a gradient approximation. With a gradient approximation, we can go. And the key about this talk is to do gradient approximations of noisy functions. This is not simple. All right, so I'm going to get there in a moment. All right, so in terms of complexity, sample everywhere. But now, if I have evaluated the function at many points, isn't it natural to save those function values, create a quadratic model of that object function, and then say, well, I'm going to move to the minimum of this quadratic model subject to a trust region. I'm not going to make wild steps because suppose that the model is concave. I put a trust region and I move that way. So I need to construct a quadratic model based on function values. This is pretty simple. How much information is there in this matrix here? N squared pieces of information. And here is about n for the gradient. So you're going to need about n squared, n is the dimension of the problem, n squared function evaluations in order to construct a quadratic model that will work well. And remember, our intuition in 2 dimensions really fools us completely. In 2 dimensions, you say, Boom, 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 I create a quadratic model. But if I have 100 variables, it becomes really difficult. So it's n squared. This can be done and has been the state of the art in derivative-free optimization for many years. Not simulated annealing, not genetic algorithms, not pattern search methods. This has been the state of the art, creating those models. There's sophistication in them in order to reduce the computational cost. It turns out that every iteration costs d to the fourth power, the dimension of the problem, the fourth power, in order to decide how to move. Now, the two main people, I think, who have promoted this area are Mike Powell, the late Mike Powell, the great figure of optimization, and Katja Scheinberg, who's now at Cornell. These two people really have led this field for about 10 years. This has been the state of the art. And I really like them. These are really great people. Therefore, I'm going to now attack them. Therefore, I'm now going to say that what they were doing is not really the right thing to do. It was an overkill. They were interpolating function values. And function values is not as good as interpolating gradient values. It's going to be better to create noisy approximations of gradients and do interpolations that way. Okay. How do we compute the gradient of a noisy function? What does it even mean, the gradient of a noisy function? So what's the noisy function? The true function is the dotted line. And I've added there some noise. This is not realistic noise, I've added that. The only thing I observe is the red function, is the red curve, right? How am I going to compute the derivative of the real function using that noisy function there? Is this possible? Is this impossible? Well, there are two ideas that came out at the same time in the last 5 years. One of them is, if you have a function that is noisy, just sample around that function and average. You smooth the function. Okay, it's a natural thing. Even in n dimensions, you get scared about sampling in a ball, but there's no free lunch. If you really want to optimize a function in 100 variables, there are so many ways to go wrong. So you have to make an effort to get the gradient, right? So one idea is to smooth the function and compute the gradient of that smoothed function. Nesterov actually wrote some theory about this. The algorithm then is very simple. You're at a point, evaluate the function many times, and then compute the gradient of that smoothed function. And the gradient is given actually by that formula that looks like a finite difference. The only difference with a finite difference is this. You take a random direction, tiny step, evaluate the function there, and compare it with the current function value, and multiply by the random direction that you have. And repeat this a number of times, and that's going to give you, the more work you put, a better approximation to the derivative of that smoothed function. This is called Gaussian smoothing. This is the algorithm. A lot of people are using that in reinforcement learning. It lends itself to that setting fairly well. Now, what we have done is something different. What we have done is said, you know, to evaluate the function in random directions may not be needed. Maybe classical finite difference approximation to the gradients will work if you only know what the finite difference in parameter should be. For a noisy function, we can do that. So I make a claim, and I'll show in a moment, that there is, for any noisy function, if you know the level of noise, the standard deviation of noise, I can tell you what the finite difference interval should be, so that the finite difference approximation will give a good approximation to the function. So here's an example. The function is smooth. Now we put uniform noise to that. And on the left is a finite difference based on the right finite differencing interval, large enough. Here is a finite difference based on too small an interval. So you're differentiating the noise. There's going to be a procedure invented by one of the great computer scientists a long time ago that is going to tell us how to find this interval, right? But do you agree that that red line is a good representation of the gradient? And this is a disaster, right? So is it going to be possible? And that's what we're going to do in our algorithm, do that estimation. Okay, so the person who came up with this idea, some of you have recognized the name, is Hamming. Hamming, the famous Hamming from computer science, says, do the following. In order to find out the finite difference interval, look at the point where you are, take a random direction, and evaluate the function, say, 7 times there. Not many times. Independently of the dimension of the problem. Take a random direction, evaluate the function, say, 7 times along that line. And then perform differences of the values that you have seen. Okay, so this is the value of the objective function at those points. I plot them there. And then I plot the difference in the function values, which is more or less the derivative. So this is the difference of those two values, and that's the difference of those two values. This is the table of finite differences. And then do it more. Then you take the differences of these differences and you put them here. So you create a table of differences, and this table finishes, right? Because at some point, you run out of that, right? Now, these numbers really should converge to 0. Why should they converge to 0? The second difference divided by h squared approximates the Hessian. But the second difference not divided by h squared should converge to 0. So if you observe this table and the numbers do not go to 0, means that you're differentiating noise. And so you see that the values here are pretty constant. At this point, what I'm doing, I'm differentiating noise. And that's enough for me to know to extract information from these columns based on a formula that he developed. Actually, it takes only a few minutes to derive. We look at these values here, which are sort of weighted averages of the columns. We look at them and see if they change. When they don't change anymore, this gives us an information on how to compute the finite difference interval, which is, sorry, not the finite difference interval. It gives you an idea of the noise level, sigma. So this is, T means column. Some weighted average of that gives us the standard deviation of the noise. And then with the standard deviation of the noise, you're going to plug it into the usual formula. By the way, I should explain, why did Hamming write a program in order to determine standard deviation of noise? Well, this is classical computer science. Computers were all over the place. They had different kinds of precision. He wanted to write a program that would detect machine precision for any number. And that's a very reliable way to do that. But what's interesting is that Moret and Wilde at Argonne said, you know, this is not just for finite precision is a way of noise. This is valid for any type of noise. And we picked up on that. And once you have it, the noise level, the formula for the differencing interval is has very simple forms. Just plug it in, you know what the finite difference interval is. And then we go one step forward. If you really have simple approximations to the gradients, why not use a quasi-Newton algorithm? Why not create a quadratic model that approximates the function? We do that here. And this is an idea that just continues to survive, this idea of quasi-Newton methods, just continues to thrive. People think like, you know, we talked about them, and then they come back. For general non-smooth optimization, quasi-Newton methods is currently considered the best algorithm. Here in this context, you only have function values. With that, we estimated gradients. Once you have these decent gradients, put them into a quasi-Newton algorithm, if you know what they are, they will construct a quadratic model that is scalable. And this LBFGS algorithm is of order D. So we did those computations. Here's the algorithm. And it works fairly well. The red line are our friends, Powell and Katia, the state-of-the-art in derivative-free optimization. And here are two versions of our algorithm, Albert Barajas' algorithm, forward and central differences. And it's working really well. This is in terms of function evaluations. In terms of total computational work, it's even more benign, because their work is d to the 4 and our work is OD, right? So this is a good thing. It worked really well. But I'm not going to use that for reinforcement learning. Reinforcement learning is too noisy. I'm going to use very, very crude approximations. So our latest results show that if you use, now I see that this thing got perturbed. And here are the typical problems for the Mujoko set. I run those problems there. And when I run them with Gaussian smoothing, using a very crude approximation to the derivative. And this is what we observe. This is Gaussian smoothing by doing at every point just evaluating one random direction, doing the differencing, and declaring that to be the gradient of the objective function. This is an extremely weak gradient. That's this line here. This line over here is full finite differences, computing the real gradient. As with neural networks, it turns out that the very noisy approximations to the gradient are working better, are giving you better results in that. Right? So I want to summarize what I said here. So multiple results about this. By the way, this area of reinforcement learning, of course, it seems to be in its infancy, right? The more I dig into, you're optimizing these functions, are they actually continuous? Are they actually, could they be discrete? What the sampling does on that. People are just throwing algorithms on them and getting results. And when I was saying, I don't know how to optimize a function in many, many variables with only function values, nobody's saying anybody's optimizing anything, right? They're decreasing the function value. And it's a complicated thing. But it was a good thing to contrast two different ideas that came from two different disciplines about how to do derivative-free optimization. So the takeaway is, if you have only function values, estimate derivatives. If you have noisy function values, estimate derivatives. Once you have estimated derivatives, give it to the gradient method. Give it to a quasi-Newton method. I think that's the way to go. All right, thanks.
All right, so we have quite a lot of time for questions also. So can people raise their hands who have questions, and you'll get a microphone.
Hi, how do you cope with noise with long tails in the distribution?
Yeah, very good. You caught me cheating there. The only analysis that we have so far for the algorithm I presented is for the case where the noise is bounded. Now, if I have tails, what would I do? If you were to work with me on a project, let's do it together. Let's look at unbounded noise. There are two possibilities. I'm going to design an optimization algorithm that can handle that, or we're going to filter out outliers. We're going to find a procedure that says don't use that information. I would go for the latter. I would take what we have here and try to see how we can get sort of Gaussian noise would give you this, right? But that was a very good question. He caught me there.
I actually have a question. So I'm wondering, because since you're doing finite differences, so as your dimension grows, I mean, practically this could become very expensive. I was wondering how this compares to, for example, using expected improvement where you have a Gaussian process, for example, fitted. And it also, I've seen that it works with noise, and then, I was wondering in your comment on that.
I think there is no cheaper way to do that. If you do Gaussian smoothing, which is a randomized process, you really have to do a lot of those random directions, right? Finite differences is. I think by nature, this problem requires, in general, unless it has structure, a lot of function evaluations. Now, there is one thing, if I can say, that I should have said at the beginning of the talk. General optimization problems, nonlinear, are really hard to solve unless there's a low-level structure of the problem that makes it possible. Almost everything that we solve, when you look at the Hessian matrix is almost low rank. There are subspaces. And that must be the case with neural networks, because otherwise you wouldn't get anywhere with that, right? So once you have only function values, you cannot discover those manifolds. So unless someone would tell you, sample in a certain way, if you have that knowledge, then you can do it in much less work. But the black box system, you cannot do it. You have to pay that tremendous price in order to get there. By the way, if I can finish just with one thing, because it is funny, now that I'm so close. I mean, I studied just there. So I was an undergraduate in physics here, theoretical physics. Fun, right? But my brother and I used to build stuff. And we built a telescope. One of those things that you build everything. You grind the mirror and you know, everything. You put it all together, and we're having fun with the telescope. We would drive out of Mexico City so there wasn't, you could see something, and our telescope would tell us pretty good stuff. And then when I was a student, I heard the Astronomy Institute here as a really good machine for grinding mirrors, right? And then I said, well, they should really grind my mirror, right? How do I do this? And so I thought, well, the only possibility is actually to volunteer to be an intern with the Astronomy Institute. So I interned with them, and after a little while, they agreed to polish our mirror. But what happened is I had to do some work, right? Mirror, you don't just go there. And my work was actually to work with a ray tracing program that they had at the time. They were designing a telescope, Ritchie-Meynier type, that has both mirrors and lenses. And the idea is to minimize aberrations, chromatic astigmatism, to optimize the quality of the image. And they had a program that had come from Kodak, the ray tracing, and then you do the optimization. And then I thought, well, this optimization sounds pretty good, right? I started looking at that optimization. I've never stopped looking at optimization since then, just because of this telescope, right?
Hello. Would you say, for example, when you have like this ray tracing or a light thing, the way like the noise that light makes, it's like a Gaussian blur, I guess, or something. So would like modeling that but running it with lenses, that would be like almost immediate, right? Like that calculation. So is there like with this optical focus, like doing optimization?
Oh yeah. In fact, the reason why you have cameras that are so good and so small is because it just got better and better, the optimization. I mean, it was just a matter of finding out how to exactly find the shape and get the materials, right? So it's just, this is all just 30 years.
Yeah, but I mean, like, you have only one lens in this stuff, like making a neural network with every Gaussian node, having it like a lens, and yeah, when you run, it goes like really fast, right?
I hadn't thought about this. So you want to run inside a neural network. Part of the operation is the ray tracing.
Yeah.
And you're going to combine it with this inner products and values.
I mean,
I have to think.
doing the lenses is really expensive, right?
Yeah.
So, but that would be like some sort of like not neural network, but like optical network that does the calculate. Well, I mean also like measuring the light. It's also like a expensive problem. I mean, to get the samples.
I think you're into something here, and I bet in the audience there are people who know much more about optics. Yes, hi.
So, just to answer your question, sorry. In MIT, Dirk Englund is a professor that uses SLMs, these light modulators, to try to solve this type of optimization problems. And they have a startup company, I forget the name, that raised about $20 million to try to do something similar. So you should check that out. Yeah.
Thank you.
I have a second question, actually. I'm taking advantage of that. So since you're getting the Hessian approximation with the BFGS, there are some techniques that you can do to get, so instead of doing finite difference in every direction, you can do like conjugate directions, and then have you looked at this again for efficiency in the sampling? Or
Conjugate directions are expensive, right? In general, if a function is quadratic, you can get conjugacy by just doing a dot product every time. Once you go from quadratic to non-quadratic, the concept of conjugacy is not well defined, and the nonlinear conjugate gradient algorithm is not that stable. So after so many years, we found that this is quasi-Newton approximations, because they have some certain overriding properties. They're very efficient. So what I mean is by the following: if you want conjugacy, which means that you want to find the basis, if you get error, even rounding error, destroys your basis. Now, if you have adversarial situations where the objective function looks like this and then it turns, then your conjugacy is all going to go out the drain, right? In a quasi-Newton algorithm, if I move from here to there and tells me that the function looks like this, and in the next step I move along the same direction, tells me the function looks very different, the last update overwrites the first update. So you don't have to combine them all together and create a basis like this. This is a very generic type of answer. Yeah.
All right. There's no more questions, then let's thank Jorge Nocedal again, please.